You're on a late 1800s downtown commercial street. Think an 1890s brick and stone bank block with a heavy cornice and a clipped rooftop skyline. You look up, and there it is, a rooftop tower that isn't really a tower, more like a thin mast rising from a small, framed platform with a crown of metalwork that people call decorative. The casual explanation is ready-made, just ornament, just a lightning rod. But the detail that breaks the story is right in front of you. Ceramic insulators, multiple of them, spaced like a deliberate isolation system, not like trim. And below, on the parapet line, you can still see repeatable bolt patterns and oxidized conductor stains, roots, not flourishes. If it's only a rod, why is it built like a small distribution point? If it's only decoration, why is it insulated? Here's the claim break. Framed as a contradiction, you're looking at the surviving shell of an obsolete building system, traceable, checkable, and documented in period language if you know what to search. By the late 1880s, downtown office buildings in Chicago and Detroit followed a recognizable pattern: heavy stone base, brick shafts rising 4 to 6 stories, elaborate cornice work marking the roofline. Banks and insurance blocks competed for architectural presence, and that presence included rooftop embellishment, finials, cresting, decorative ironwork. But walk down any preserved commercial street from that era, and you'll notice something odd about certain rooftop features. They're too functional-looking to be purely decorative, yet too elaborate to be simple utility hardware. Take a standard example. A slender mast rising from a small wooden or iron platform bolted to the roof deck, topped with a symmetrical arrangement of metal arms spreading outward like a crown. The first thing people notice is the silhouette. Dramatic, Gothic, attention-grabbing. The second thing, if they look closer, is the hardware. Multiple ceramic spool insulators, the kind used to isolate electrical conductors, are mounted at regular intervals along the mast and arms. Each insulator sits on a metal standoff precisely spaced, with clamps or terminals at the top. The official story is straightforward. It's a lightning rod, possibly with decorative flourishes added for architectural effect. Lightning protection was a serious concern for valuable downtown buildings, and elaborate rod installations were common. But here's where the physical evidence starts to pull away from that explanation. A lightning rod's primary job is to provide a single, direct path from the highest point of a building to the ground. The standard configuration is one dominant down conductor, often a heavy copper or iron cable, running as straight as possible to a buried ground plate or water pipe connection. The goal is simplicity and conductivity, one clear route for the electrical discharge. What you're looking at has something different. Multiple insulated points, symmetrical metal arms creating an array rather than a single collection point, and conductor routing that doesn't head straight down the exterior wall. Instead, weathering patterns on the masonry, faint streaks of oxidation, track horizontally along the parapet edge before turning inward at specific points. And these are paths, not random staining. They suggest conductors that ran along the roof perimeter and then penetrated the building envelope at deliberate locations. Count the insulators. On a typical surviving example, you might find 6 to 12 ceramic pieces, all the same type, all deliberately spaced. Compare that to a true single-rod lightning installation on the next block. You'll usually see 1 or 2 insulators at most, often none if the rod is directly grounded. The insulation isn't needed for basic lightning protection. It's needed when you want to isolate conductors from each other or from the building structure itself. That's a different engineering requirement entirely. Period lightning protection guides from the 1880s and 1890s are surprisingly specific about installation standards. Insurance underwriters publish detailed recommendations: rod diameter, conductor gauge, ground plate specifications, inspection procedures. These documents emphasize single-path grounding and minimal complexity. The rooftop arrays with multiple insulators and symmetrical layouts don't match those specifications. They resemble something else, something that required isolation and distribution rather than simple dissipation. If these are just for lighting, where's the straightforward ground path? Why the array? While you're noticing the rooftop tower, drop your eye to the brick line below. See those ceramic mounts. Pre-1920 mid-rise hotels and apartment blocks offer some of the clearest evidence of what these systems look like at the building envelope. The roofline is where the public face meets the functional infrastructure. And that's where the contradictions become impossible to ignore. Look at the parapet coping, the stone or terracotta cap that crowns the brick wall. On buildings from this era, especially those with surviving rooftop hardware, you'll often find small, drilled penetrations through the coping stones, each sealed with lead or bitumen patches. These aren't random, they're systematically placed, often near corners or at regular intervals along the wall. Each penetration corresponds to a ceramic insulator mounted on the exterior face of the parapet, held in place by a metal standoff bracket bolted through the stone. The insulators themselves are immediately recognizable once you know what to look for. White or brown porcelain spools, each with a central hole for the mounting bolt and grooves around the circumference for holding a conductor. And the glaze is often crazed from decades of weathering, and the mounting hardware shows the reddish-brown staining of oxidized iron. At the top of each insulator, you'll sometimes still see a wire clamp or terminal, a small metal saddle designed to hold a conductor firmly in place without touching the building structure directly. This is where the ornament explanation starts to collapse. Decoration doesn't need penetration sealed like utility pass-throughs. When architects added purely visual elements to rooflines, cresting finials, carved stone panels, they mounted them on the exterior surface or embedded them into the masonry during construction. They didn't drill through finished coping stones and seal the holes with waterproofing compounds. That's the signature of a functional penetration. Something that had to pass through the building envelope while maintaining weatherproofing and structural integrity. Lightning rods, for their part, rarely require multiple insulated feed-throughs at parapet height. A standard installation brings a single down conductor from the rooftop collection point straight down the building's exterior, usually at a corner or along a downspout. If it penetrates the building at all, it's typically near the foundation to reach a ground connection. The parapet-level penetrations with individual insulators suggest something else: conductors entering the building at the roofline and routing through the interior. Building trade catalogues from the 1890s through 1910s, dusty volumes preserved in technical libraries and historical societies, show hardware that matches these installations exactly. Sections labeled roof fittings, insulators and brackets, and conductor supports include detailed engravings of ceramic insulators on metal standoffs, conductor clamps, and penetration seals. The catalogue language is matter-of-fact, treating these as standard components for specific applications, not as decorative accessories or lightning rod embellishments. Here's the verification step anyone can take. Look for patched holes below the insulator line. Those are utility scars. Find a pre-1920 hotel or apartment building with original roofline details. Stand across the street with good light and examine the parapet. The patches are usually a different color or texture than the surrounding stone, slightly darker, sometimes with a different surface finish, where the sealant weathered differently than the original masonry. Each patch marks a point where something passed through the wall, ran along or through the building's interior structure, and connected to something inside. If something passed through the roof edge, where did it go inside? Turn-of-the-century municipal buildings, city hall annexes, courthouse wings, post offices, were built to project permanence and authority. These were substantial structures with tall ceilings, thick walls, and formal interior layouts designed for public access and bureaucratic function. They were also, it turns out, excellent places to look for interior evidence of systems that entered through the roofline. Start in an upper corridor or attic space if access is available. You're looking for something specific, a rectangular shadow on the plaster wall, usually between 5 and 7 feet off the floor, about 2 to 3 feet wide and 3 to 4 feet tall. The shadow isn't a stain exactly, it's a zone where the plaster is a slightly different color or texture, often with a clean geometric edge that suggests something was once mounted there and later removed. Around this shadow you'll typically find a pattern of screw holes or bolt holes, sometimes filled in but still visible as small circular patches in the plaster. These are cabinet ghosts, the marks left when a piece of equipment was unbolted from the wall and the mounting points were patched over. The geometry is too consistent to be coincidental. Measure the bracket spacing on multiple buildings and you'll find repeating dimensions. Mounting holes at 16-inch intervals, top and bottom rows aligned horizontally, side mounting points suggesting a frame or enclosure about 6 inches deep. This is standardized hardware, not improvised installation. What makes these mounting points significant is what they're not. They don't match the hardware patterns for early electrical distribution panels, which typically had different dimensions, different mounting logic, and conductor entry points at the bottom rather than the top. They don't match the footprint of later telephone or signal equipment, which evolved different standard sizes and mounting practices. They don't match gas fixture installations, radiator connections, or any other common building system from the era. There's something specific, and that specificity repeats across buildings from the same period. Look at the conduit stubs, short sections of metal tube protruding from the wall or ceiling, now capped or cut off, often painted over multiple times. On buildings where the interior routing is still partially visible, these stubs lead upward toward the roofline or outward toward exterior walls where the parapet penetrations are located. The routing doesn't follow the paths you'd expect for standard electrical distribution, which typically ran from basement service entries upward through the building via vertical chases in stairwells or utility cores. These routes suggest entry from above, collection at a central point, and limited local distribution, a different topology entirely. Municipal maintenance notes and procurement line items from the 1890s through 1910s occasionally reference this equipment in frustratingly generic terms: apparatus, insulators, conductors, roof connections. Without more context, these entries are easy to overlook or misinterpret as standard electrical hardware. But when you pair the procurement language with the physical evidence, the cabinet mounting points, the roofline penetrations, the conductor routing, the pattern becomes clearer. Something was systematically installed, systematically maintained, and eventually systematically removed. Here's the investigative challenge. Ornament doesn't leave standardized interior mounting geometry. Decoration stays on the exterior envelope. Lightning down conductors don't usually terminate into cabinet-like fixtures. They run straight to ground. The mounting patterns you're looking at imply equipment that required regulated access, some form of interior housing, and careful isolation from the building structure. That's not ornament, and it's not simple lightning protection. That's something else. Measure the bracket spacing. Compare across buildings from different cities built in the same era. If you find the same dimensions appearing independently, same cabinet width, same mounting hole intervals, same conductor entry points, you're looking at evidence of a standardized system that was once common enough to have repeatable installation practices. If it's random, why do different cities show the same cabinet footprint? Brick textile mills and light manufacturing buildings from 1880 to 1910 offer a different perspective on the same infrastructure pattern. These were large footprint structures, often multi-story, built in New England mill towns and across the Rust Belt, when water-powered and early electric industrial operations coexisted. The buildings themselves are architectural survivors: solid construction, high ceilings for machinery installation, tall windows for natural light, and roof lines that still show traces of systems that nobody talks about anymore. From street level, look at the roof geometry. Mills typically had shallow pitched roofs or flat roofs with parapet walls, and on many surviving examples you'll see small masts or frameworks rising from specific locations, building corners, center ridge lines, and points along the roofline that align with interior stair towers or service cores. The placement isn't random. It follows a logic that makes sense if you're thinking about distribution pathways rather than decoration or lightning protection alone. Lightning protection, when it was installed on industrial buildings, tended to prioritize perimeter coverage and direct grounding. The goal was to protect the structure itself and prevent fire risk from lightning strikes hitting tall brick walls or exposed roof framing. Rod installations focused on creating the shortest path to ground, often running down external corners where downspouts were located. The rooftop masts you're seeing on these mills have a different orientation. They're positioned to align with interior vertical circulation: stair towers, elevator shafts, utility chases. The conductor stains on the masonry don't run straight down the exterior walls. They track toward these service cores, suggesting interior routing. Plot these locations on a city map for any surviving mill district, and you'll see the pattern repeat by building type. Large rectangular mill buildings get rooftop installations at corners and mid-span points corresponding to interior structural bays. Narrower factory wings get single, central installations aligned with the main stairwell. Office annexes attached to production buildings often have their own separate rooftop hardware, suggesting independent systems or different distribution needs. The placement pattern is too consistent to be coincidental, too functionally aligned with building layout to be purely ornamental. Engineering journals and plant maintenance ledgers from this period, preserved in industrial archives and historical society collections, occasionally reference roof apparatus and instrument circuits in ways that suggest these installations had practical operational purposes beyond aesthetics or lightning protection. Factories kept detailed maintenance records because insurance requirements and operational efficiency demanded it. When entries mention insulator replacement, conductor inspection, or apparatus testing on regular schedules, that's evidence of functional infrastructure, not decorative ironwork. Factory insurance inspections from the early 1900s add another documentation layer. Underwriters were intensely concerned with fire risk, electrical hazards, and structural safety in industrial buildings. Inspection reports categorized building systems and equipment systematically: boiler installations, electrical services, fire suppression, mechanical power transmission, and a catch-all category often labeled auxiliary apparatus or protective devices. The language is generic, but the inspection requirements were specific: clearances from combustible materials, proper insulation, grounding provisions, and regular testing. Decoration didn't get inspected, systems did. Here's the geographic verification. Map the locations of surviving rooftop masts across a mill town or industrial district. Note the building construction dates and the positions of the installations. Check whether similar buildings from the same era in different cities show the same placement logic. If independent builders in different regions arrived at the same rooftop positions and the same alignment with interior service cores, that suggests they were following either a common standard or solving a common functional requirement. Either way, it's pattern, not coincidence. Compare this to true perimeter lightning rod installations on adjacent buildings, commercial blocks, or civic structures that prioritized exterior path to ground. The hardware looks different, the mounting logic is different, and the conductor routing is different. The factory installations align with interior distribution infrastructure. The lighting installations prioritize exterior grounding. Both might use insulators, both might have rooftop collection points, but the underlying system logic diverges. Why would banks, hotels, and factories converge on the same rooftop layout if they weren't addressing a similar functional need? Downtown core buildings from roughly 1890 to 1915, banks with secure vault areas, hotels with public rooms and guest corridors, municipal buildings with office wings, show how the same infrastructure adapted to different functional requirements. The rooftop hardware might look similar from street level, but the interior routing tells a more specific story about what each building type needed from the system. Banks are particularly revealing. These were high-value buildings with thick walls, reinforced vault rooms, limited window penetration for security, and careful attention to any system that required interior access points. The conductor routing you can still trace in some surviving structures tends towards central corridors rather than perimeter walls, often with paths that run toward vault anterooms or cashier areas, spaces where instrument panels or regulated equipment would make operational sense. The placement suggests the system served specific functional zones, not whole building distribution. Hotels present a different pattern. The conductor routes cluster near main public rooms, lobbies, dining halls, reading rooms, and near main stairwells. They avoid the warren of small guest rooms that filled most of the building's floor area. This selective distribution is significant. If the system were providing general lighting power or building-wide electrical service, you'd expect to see routing infrastructure extending into guest room corridors. Instead, the evidence suggests limited endpoints concentrated in public and service areas where operational visibility or instrument monitoring might matter. Municipal buildings, courthouses, city halls, post office branches show routing concentrated in main corridors and near administrative office clusters. The paths avoid storage rooms, mechanical spaces, and less formal areas. Again, the pattern suggests selective coverage, not comprehensive building service. Whatever the system provided, it served specific locations within each building rather than every room. Building codes and safety standards from this era, preserved in municipal archives and engineering libraries, occasionally reference conductors, insulation, and apparatus rooms in ways that distinguish these installations from standard electrical service or lightning protection. The terminology is careful. Codes that address building electrical systems use different section headings and different technical language than codes addressing lightning protection. And both of those categories are distinct from sections covering what period documents sometimes call auxiliary circuits or atmospheric apparatus. The distinctions matter because they reflect different installation requirements, different inspection protocols, and different functional expectations. The mounting points in these buildings, those cabinet ghosts and bracket patterns, cluster near stairwells and attic runs, which makes sense if you're thinking about vertical distribution from a rooftop entry point. You'd want easy maintenance access, proximity to vertical chases that simplify conductor routing, and locations where equipment installation wouldn't interfere with finished public spaces. The logic is practical, not decorative. Here's a comparative exercise anyone can do with access to period buildings. Examine attic framing above main corridors in structures from this era. Look for added cleats or standoffs, small wooden or metal brackets fastened to joists or rafters that aren't part of the structural framing. These are conductor supports added after initial construction to route wires or cables along specific paths. They're usually easy to distinguish from structural members because they're smaller, more crudely attached, and placed at intervals that correspond to conductor sag rather than load-bearing requirements. If you see these supports running from a roof penetration point toward a specific interior location, you're looking at a distribution path. The comparative evidence across building types becomes compelling when you see the same component geometry, same insulator sizes, same mounting hardware, same cabinet dimensions, installed with function-specific routing, central corridors in banks, public rooms in hotels, administrative wings in municipal buildings. The hardware is standardized, but the routing adapts to building needs. That's system thinking, not decoration. The question this raises is functional. If it distributed something, what did the system need at the roof? What kind of infrastructure requires rooftop collection, careful insulation, regulated interior access, and selective distribution to specific building zones? The answer isn't immediately obvious from the hardware alone, but the pattern of requirements starts to narrow the possibilities. Early 20th century schools, brick structures with long corridors, tall attic spaces, and standardized layouts driven by educational function and fire safety codes provide some of the clearest interior evidence of how these systems were installed. Schools were built to last, built to code, and built with access for maintenance, which means interior infrastructure often remained visible longer than in buildings that underwent more frequent renovations. Start in the attic space above classrooms if the building still has accessible attic runs. You're looking for ceramic bushings through floor joists, small porcelain tubes, usually 1 to 2 inches in diameter, inserted into drilled holes through the wood. These bushings insulated conductors passing through structural members, preventing direct contact between the conductor and the wood. This is a specific installation practice. If you were running early electrical wiring for lighting, you'd used knob and tube methods with standardized spacing and routing rules. The bushings you're seeing in these schools appear in different patterns, localized clusters near roof penetration points rather than continuous runs through the entire attic space. Look for standoff mounts attached to rafters or collar ties, small porcelain knobs on metal or wooden brackets spaced irregularly, holding conductors away from the building structure. Again, this looks superficially similar to early electrical wiring, but the details diverge. Knob and tube had specific code requirements for spacing, typically 4 to 6 inches off the surface, and routing, following predictable paths from service entry to fixture locations. What you're seeing in these attic spaces has different characteristics: tighter clusters of standoffs near specific entry points, routing that leads toward localized equipment zones rather than distributed fixture locations, and occasionally leftover hardware that doesn't quite match standard electrical components. Some of these leftover pieces are particularly telling: porcelain knobs with unusual profiles, ceramic supports with mounting geometries that don't match standard electrical catalog offerings, and conductor clamps designed for wire gauges or configurations that seem odd for lighting circuits. These are specialized components, and when you find them clustered near roof penetration points and cabinet mounting locations, they suggest specialized applications. Electrical installation manuals from 1900 to 1925, preserved in trade school libraries and electrical contractor archives, provide useful comparison material. These manuals are remarkably detailed, showing standard practices for residential and commercial wiring with specific diagrams for fixture installation, service panel configurations, and conductor routing. When you compare the manual diagrams to what you're actually seeing in these school attics, the differences become apparent. The attic installations have different hardware profiles, different clustering patterns, and different routing logic. They're not following the same installation rules. Patent drawings from the 1890s through 1910s offer another layer of comparison. This was a high patent era for anything related to electrical, telegraph, telephone, and atmospheric electricity systems. Patent records include detailed schematic plates showing component arrangements, mounting methods, and system configurations. Search for patents related to insulators, conductor supports, switchboards, or rooftop terminals, and you'll find hardware that matches the physical evidence in these schools more closely than standard electrical equipment does. The patent language is often revealing. Terms like atmospheric terminal, collection array, isolation apparatus, and regulatory device appear in descriptions that specify rooftop mounting, insulated conductor paths, and cabinet-mounted equipment for conditioning or regulating whatever the system collected. The constraint framing matters here. These were not high-power systems. The conductor gauges are too light, the cabinet footprints are too small, and the distribution paths are too limited to support whole-building electrical loads. Whatever these systems did, they operated at low power, served specific endpoints, instrument panels, indicator lamps, charging circuits, signal devices, and required regular maintenance, exactly the kind of infrastructure that becomes obsolete when more reliable, standardized alternatives become available. Here's the verification exercise. Photograph the insulator types still present in accessible attic spaces, document the mounting hardware profiles and the conductor routing patterns. Then compare those photographs to period electrical equipment catalogues and patent drawings. Look for matches not in the modern names, which might not exist for obsolete components, but in the physical shapes, the mounting geometries, and the functional arrangements. The hardware tells the story even when the labels have been lost or changed. If it's not standard lighting power, what was it supplementing, and why did schools, along with banks, hotels and factories, install similar rooftop-to-interior infrastructure during the same period? Let's anchor this investigation with specific building types that anyone can still examine today. Pick any regional cluster of turn-of-the-century commercial and institutional buildings, a preserved downtown district in the upper Midwest, a mill town in New England, a county seat with surviving late Victorian civic structures. Within a few blocks, you'll likely find 3 or 4 buildings that demonstrate the pattern with unusual clarity. First anchor, an 1890s bank building, probably 3 to 5 stories, brick with stone trim, elaborate cornice work, corner location. Check the roofline for a surviving mast installation. It might be weathered, partially dismantled or painted over, but the mounting platform and primary vertical element are often still present because removing them costs more than leaving them in place. Photograph the rooftop mast base from an adjacent building or with a telephoto lens. Measure the bolt pattern if access allows. You're looking for a square or rectangular platform, probably 18 to 24 inches on a side, bolted through the roof deck with anchor points on 12 to 16-inch centers. The mast itself rises from the center of this platform, typically a metal tube or framework 1 to 3 inches in diameter and 6 to 12 feet tall. Now look at the ceramic insulators. On a well-preserved example, you might count 6 to 10 ceramic spools, each 2 to 4 inches tall, mounted at regular intervals along the mast and on symmetrical arms extending outward. Each insulator sits on a standoff bracket that holds it several inches away from the metal structure. Check for conductor clamps at the top of each insulator, small metal saddles or binding posts designed to secure a wire without allowing it to touch the mast itself. Note any weathering patterns on the surrounding roof surface, oxidation stains, discolored metal, or conductor pathways traced in subtle variations of rooftop patina. Second anchor, a 1905 hotel, probably 4 to 8 stories, brick or brick and terracotta, located on a main commercial street. The rooftop hardware might be less intact than the bank example, but check the parapet line for evidence of conductor penetrations. Look for ceramic insulators mounted on the exterior face of the parapet wall, often near corners or at regular intervals of 20 to 40 feet. Each mounting point should show a bolt passing through the parapet coping with weatherproofing patches around the penetration. Inside, if attic access is possible, trace the conductor paths from these penetration points inward. They should lead towards central corridors or stair towers rather than distributing throughout the building. Third anchor, a 1910 factory or light industrial building, probably 1 to 3 stories with large floor area, located in a former manufacturing district. The rooftop installations on these buildings often show the clearest system logic because industrial structures prioritized function over ornament. Look for masts positioned at structural intervals, corners and mid-span points along ridge lines, with conductor routing that aligns with interior column lines or service chases. Measure the spacing between rooftop installations. It should correlate with building bay dimensions rather than with decorative rhythm. Fourth anchor, a 1912 municipal annex, a courthouse wing, city hall addition, or post office branch. These buildings typically have excellent documentation, original construction permits, periodic roof repair approvals, and insurance inspection forms that might reference apparatus or roof equipment in ways that distinguish it from standard building systems. The rooftop hardware on municipal buildings often survived longer than on commercial structures because public buildings had slower renovation cycles and less economic pressure to modernize. Here's the critical observation. Measure the rooftop mast base dimensions across all 4 buildings. If they're identical or very close, same bolt pattern, same platform size, same mounting logic, you're looking at standardized installation practices. Measure the ceramic spool sizes. If they match across independent buildings in different functional categories, that's evidence of common component sourcing. Check the conductor routing patterns. If banks, hotels, factories, and municipal buildings all show conductors entering the building at the roofline and routing towards central equipment locations, that's system topology, not coincidence. City permit records and roof repair approvals sometimes survive in municipal archives or county clerk offices. These are public records accessible through standard research request procedures. Look for entries from 1890 to 1920 that reference roof apparatus, conductor installation, insulator replacement, or generic terms like metalwork that might encompass functional hardware as well as decorative elements. The documentation exists, it's just filed under language that seems unremarkable until you know what you're looking for. You can still see this today from street level. You can request permit cards. You can check historic photographs for before renovation images that might show the systems more intact. The evidence is there, physical, documentary, and photographic. Independent builders made these installations following repeatable patterns, which means either they were copying each other or they were following a common standard. If independent builders made decorations, why do the mounting geometries look standardized across different cities, different architects, and different building types? If these installations were real functional systems rather than ornament or simple lightning protection, specific categories of records must exist, and they do if you know where to look and what language to search for. The challenge is that obsolete technologies don't always carry forward their original names. The terminology shifts as memory fades and as new systems replace old ones. Start with procurement records, municipal purchasing archives, institutional building files, and construction bid specifications from 1890 to 1920. These documents are remarkably detailed because public money and institutional oversight required documentation. Look for line items that don't fit standard categories. Roof terminal apparatus, insulator assemblies, conductor hardware, cabinet fixtures. The descriptions are often generic: metalwork, roofing specialties, electrical apparatus, but the quantities and unit prices provide clues. If a single building renovation includes 24 ceramic insulators, multiple lengths of specific gauge conductor, and a cabinet with regulatory apparatus, that's a bill of materials for a small system installation, not decoration. Trade supply catalogues from the late 19th and early 20th centuries are gold mines of physical evidence. These catalogues, Thick volumes printed for contractors, electricians, and building managers show product illustrations with detailed specifications, dimensional drawings, materials, mounting methods, and typical applications. Library special collections and historical society archives often have substantial catalogue collections, and many have been digitized for research access. Search catalogue categories systematically. Roof fittings, insulators, conductor hardware, switchboard equipment, lightning protection, and auxiliary apparatus. The last category is particularly interesting because it served as a catch-all for systems that didn't fit standard electrical or telegraph classifications. Page through these sections looking for component shapes that match what you've observed on buildings: ceramic spool insulators, metal standoff brackets, rooftop terminal assemblies, conductor clamps, and cabinet-mounted equipment with multiple insulated input terminals. When you find matches, read the product descriptions carefully. The catalogue language is usually straightforward. Manufacturers weren't selling mystery, they were selling functional components to professional buyers who needed specific hardware for specific applications. Terms like atmospheric collection, isolation mounting, rooftop terminal, and regulatory apparatus appear in contexts that specify installation locations, rooftop mounting, parapet placement, attic routing, and functional requirements, insulation from building structure, multiple conductor paths, controlled distribution. The functional interpretation you can draw from this documentation is measured but clear. Rooftop installations served as receiving or collection points. Ceramic insulators provided electrical isolation between conductors and building structure. Cabinet-mounted equipment regulated, switched, or conditioned whatever was collected. Interior conductor routes distributed to limited endpoints, possibly instrument panels, charging circuits, indicator lamps, or signaling devices. This is low-power supplemental infrastructure, not primary building electrical service. Patent records provide another documentation layer, searchable through National Patent Office databases and historical patent collections. The 1890s through 1910s saw intensive patent activity around anything related to electricity, atmospheric phenomena, communication systems, and building utilities. Search for patents covering rooftop terminals, atmospheric collection apparatus, insulated conductor arrays, protective switching devices, and related terms. The patent drawings are particularly valuable. They show mounting methods, conductor arrangements, isolation strategies, and system configurations with engineering precision. Here's a verification strategy that works even without specialized research access. Search for the hardware shapes, not the modern names. Take photographs of rooftop mast configurations, insulator profiles, and mounting hardware from surviving installations. Then page through digitized period catalogues and patent drawings looking for visual matches. When you find a component that looks identical, same dimensions, same mounting geometry, same insulator placement, read the description to see what it was called and what it was intended for. The hardware taxonomy tells you what the system was, even if the memory of its function has faded. The reason this documentation matters is that it bridges the gap between physical evidence and functional interpretation. You can observe mounting hardware and conductor routing. You can document repeatable patterns across building types. You can demonstrate that the installations don't match standard electrical or lightning protection practices. But without period documentation, you're left with, it looks like it did something rather than here's what it actually did. The documentation exists catalogued under period terminology, and it describes systems that match the physical evidence you're observing. One constraint to acknowledge, the documentation often uses generic language, apparatus, auxiliary equipment, protective devices that could refer to multiple different systems. The specificity comes from combining documentation types. When procurement records list rooftop terminals with insulators, when catalogue plates show matching hardware, when patent drawings specify rooftop mounting and isolated conductor arrangements, and when building code references address atmospheric collection installations, the accumulated documentation points toward a specific system category rather than vague possibilities. The evidence suggests a small, supplemental system designed around rooftop collection of atmospheric electricity, what period sources sometimes called earth currents or atmospheric potential, with careful isolation, cabinet-mounted regulation or conditioning, and limited distribution to low-power endpoints. The infrastructure was real, documented, commercially available, and systematically installed across building types during a specific historical period when such supplemental systems seemed practical before grid standardization made them obsolete. If it was a system, why did it need isolation like this, and what does period documentation actually call it? Patent filings from 1890 through 1915 contain surprisingly detailed technical diagrams that, when compared to surviving physical installations, provide the clearest documentation of what these systems were and how they worked. Patents are useful not just because they describe inventions, but because they show functional arrangements and mounting methods with engineering precision, exactly what you need to translate shapes on rooftops into named components and system logic. Start with patent classifications for atmospheric electricity and lightning protection and similar systems, but expand to adjacent categories like electrical distribution, switching and regulation, and building electrical systems. The patent documents typically include multiple schematic plates showing rooftop terminal configurations, insulator placement and spacing, conductor routing from collection points to interior equipment, cabinet-mounted regulatory devices, and distribution arrangements to endpoints. Look for specific component terminology that appears repeatedly across patents from this era. Terminal or collection terminal, the rooftop array structure, insulator or isolation support, ceramic standoffs, arrestor or protective device, equipment to regulate voltage or prevent overload, switchboard or distribution panel, cabinet-mounted control equipment, and conductor or lead, the wiring that connected components. These terms are consistent across patents, suggesting common technical language within the field. The crown-like terminal shapes you see on rooftops match patent drawings for atmospheric collection terminals or elevated capture devices. Designs intended to maximize exposure to atmospheric potential by presenting multiple points at elevation, symmetrically arranged, and carefully insulated from the building structure. The multi-point array isn't decorative, it's functional geometry designed to increase collection surface area while maintaining electrical isolation between collection points and ground. Patent descriptions often specify mounting requirements: terminal to be erected on rooftop, conductors to pass through building envelope with proper insulation, routing to interior cabinet for regulation. The language is precise about isolation needs. Conductors must be insulated from building structure to prevent unintended grounding, ceramic standoffs must provide adequate clearance, and cabinet equipment must include protective devices to prevent voltage spikes from damaging connected apparatus. Compare patent bolt spacing and platform dimensions to what you measured on actual buildings. If a patent from 1895 specifies a terminal base of 18 inches square with mounting bolts on 14-inch centers, and you find surviving installations with exactly those dimensions, you've linked documentation to physical evidence. If a patent shows ceramic insulators spaced at intervals of 24 to 36 inches along conductor runs, and you observe the same spacing patterns in building attics, you're seeing standardized installation practices derived from documented system requirements. The constraint framing in these patents is revealing. They describe low-power systems typically operating at modest voltages, intended for supplemental rather than primary building electrical service. Typical applications mentioned include battery charging, instrument operation, indicator lamps, signal circuits, and telegraph equipment. And these are all low-current applications that could benefit from supplemental power sources in an era when grid electricity was expensive, unreliable, or unavailable in some locations. Some patents explicitly address atmospheric potential collection for building electrical supplementation, or earth current capture for auxiliary power. The language can seem odd or overly optimistic to modern readers familiar with reliable grid power, but the historical context matters. In the 1890s and early 1900s, electrical service was often limited to certain districts or certain hours. Backup systems and supplemental sources had practical value. These patents describe real engineering attempts to capture ambient atmospheric electricity, a genuine physical phenomenon for small-scale building applications. Schematic plates in these patents show complete system arrangements, rooftop array, insulated conductors, protective arresters, storage, regulation equipment, distribution to endpoints. Compare these schematics to the physical evidence you've documented: rooftop masts with multiple insulators, conductor paths entering through parapet, cabinet mounting locations in corridors, limited distribution routes to specific interior points. The system topology matches. One important limitation: atmospheric electricity collection systems were inherently low power and unreliable. The patents often include qualifying language about supplemental or auxiliary function, acknowledging that these systems couldn't replace primary building electrical service. As grid power became more widespread, more reliable, and more economical during the 1910s and 1920s, the practical justification for maintaining atmospheric collection infrastructure evaporated. The systems became obsolete not because they didn't work, but because better alternatives made them unnecessary. The verification step here is straightforward. Access patent databases. Many historical patents are now digitized and searchable. Look for patents covering rooftop electrical terminals and atmospheric collection systems from 1890 to 1915. Compare the patent drawings to photographs of surviving installations and check whether component dimensions and mounting methods match. When you find patent plates that look like they're diagramming the exact hardware you're seeing on buildings, you've documented not just that the systems existed, but what they were intended to do. The patent language provides one more critical piece of evidence. It shows that contemporaries understood these systems as functional infrastructure, not ornament. The inventors were engineers and electricians, not architects. The patent applications emphasize utility and performance, not aesthetics. When you see decorative-looking ironwork on a rooftop and wonder if it's really just for show, patents that document identical hardware as atmospheric collection terminals with specified electrical characteristics settle the question definitively. If it's low power and maintenance heavy, why did substantial buildings, banks, hotels, factories, municipal structures bother installing it at all during this specific historical window? Insurance underwriting records and building code provisions from 1900 through 1925 reveal why institutions cared about these installations enough to maintain them systematically, even though they represented supplemental rather than primary infrastructure. The answer lies in risk management, operational redundancy, and the specific economic and technical context of early electrification. Banks and hotels faced particular pressure from insurance underwriters who assessed fire risk, operational reliability, and business continuity planning. Buildings housing valuable assets or serving critical public functions were evaluated more strictly than ordinary commercial structures. Insurance inspection reports from this era, preserved in underwriting company archives and regulatory collections, categorized building systems and equipment systematically with separate sections for different risk categories. Look at the language in these inspection reports. Sections covering electrical apparatus distinguish between primary building service, lighting, power distribution, heating, and auxiliary equipment or protective devices. The auxiliary category includes a range of systems that provided operational redundancy or special purpose functions: emergency lighting, signal circuits, battery backup systems, telegraph equipment, and, in some reports, atmospheric apparatus or supplemental charging circuits. The inspection criteria are revealing. Auxiliary systems required adequate insulation from building structure, proper clearance from combustible materials, approved protective devices, and regular testing and maintenance. These aren't aesthetic requirements, they're safety and functionality standards. Decoration doesn't get insulated, doesn't need clearance from combustibles, and doesn't require protective devices or testing schedules. Systems do. Building codes from the same period, accessible through municipal archives and historical code collections, show similar categorization. Electrical codes had specific sections addressing lightning protection, emphasizing direct grounding paths and conductor gauge requirements, and separate sections addressing auxiliary electrical apparatus with different installation standards. The auxiliary apparatus sections specify isolation requirements, cabinet housing standards, conductor routing methods, and separation distances, exactly the installation characteristics you observe in surviving physical evidence. The separation distances matter. Code provisions often required auxiliary apparatus to maintain specific clearances from primary building electrical systems, from gas fixtures, and from combustible materials. Cabinet installations needed to be accessible for maintenance, but isolated from high traffic areas. Conductor routing through attics and wall cavities required fire-resistant conduit or substantial clearance from wooden structural members. These requirements shaped where and how the systems were installed, and they explain some of the physical patterns you observe: why cabinets cluster in specific corridor locations, why conductor routes follow particular paths, why rooftop terminals are positioned where they are. Underwriting companies had economic incentives to document these systems carefully. Properly installed and maintained auxiliary equipment could reduce fire risk, improve operational reliability, and lower claim likelihood. Buildings with backup lighting or emergency signaling systems received more favorable insurance terms in some cases. The documentation that resulted, inspection checklists, apparatus inventories, its maintenance schedules, provides indirect confirmation that these installations were functional infrastructure serving risk management purposes. Contrast this documentation with how purely decorative architectural elements were treated. Ornamental ironwork appears in inspection reports under building construction or exterior features, with criteria focused on structural adequacy and weather resistance, not electrical characteristics or maintenance schedules. Lightning protection appears under its own specific category, with clear installation standards emphasizing grounding paths and conductor specifications. The auxiliary apparatus category is distinct from both, with its own technical requirements and inspection protocols. Here's a verification approach. Request historical insurance inspection records for specific buildings if they're available through municipal archives or historical society collections. Look for how rooftop installations and associated equipment are categorized. If they're listed under apparatus or equipment, with maintenance schedules and safety requirements, that's documentation of functional systems. If they're listed under ornamental features or architectural elements that would support the decoration interpretation. The inspection categorization reflects how contemporaries understood these installations. Code language provides another layer of evidence. Period building codes sometimes specify atmospheric collection apparatus or earth current systems as a distinct category requiring specific installation methods. Codes don't explain what these systems do in detail. They assume professional readers understand the technology, but they do specify how to install them safely. Compare code requirements to physical evidence. If codes require ceramic insulation with minimum 1-inch clearance, and you observe ceramic insulators mounted on standoffs providing exactly that clearance, you're seeing code-compliant installation of documented system types. The critical question is why institutions invested in these systems despite their limitations. The answer lies in the transitional nature of early electrification. Grid power was spreading but not yet universal or reliable. Primary building electrical service could be expensive to install and operate. Supplemental systems that reduced dependence on costly grid power had economic value. As grids became more reliable and economical during the 1910s and 1920s, that economic calculus shifted. Maintenance costs for atmospheric collection systems, inspections, testing, component replacement, technical expertise increasingly outweighed the modest benefits. The systems became economically obsolete. The insurance and code documentation shows these systems were real, systematically installed, regularly inspected, and maintained until economic and technical changes made them impractical. The inspection categories prove contemporaries understood them as functional apparatus, not decoration. The maintenance schedules prove they required ongoing attention and had operational significance. The safety requirements proved they involved electrical characteristics that needed professional management. If it was inspected as functional apparatus once, documented in codes, and maintained on regular schedules, why is it called decoration now, and when did that reinterpretation happen? The practical function of these systems, what they actually did on a day-to-day basis, can be clarified without speculation or overstatement by staying close to documented applications and the physical constraints of the technology. The key is to understand both the capabilities and the severe limitations of atmospheric electricity collection as it was practiced during the 1890s through 1910s. Atmospheric electricity is a real phenomenon. The Earth's surface and the upper atmosphere maintain a voltage potential difference, typically 100 to 300 volts per meter of elevation under normal clear sky conditions, increasing dramatically during disturbed weather. This potential has been measured and studied since the 18th century and is not controversial. The question isn't whether atmospheric electricity exists, it does, but whether it could be collected and used for practical building applications at scales that justified the installation and maintenance costs. The systems you're observing on buildings were designed to capture this potential through elevated terminals, insulate it from ground through ceramic standoffs, route it through conductors to interior equipment, and condition or regulate it for specific low-power applications. Period engineering journal articles, searchable in technical library databases, discuss experimental and commercial atmospheric collection systems with varying degrees of optimism, but most acknowledge significant limitations: low power output, high variability, depending on weather and atmospheric conditions, need for storage or conditioning equipment, and suitability only for modest loads. What could these systems practically power? The physical evidence suggests limited endpoints: a few lamps, instrument panels, battery charging circuits, or signaling devices. The conductor gauges are too light for high current loads, the cabinet footprints are too small for large-scale distribution equipment, the routing patterns serve specific interior locations rather than whole building coverage. This matches documented applications from period sources: indicator lamps that monitored system status, low-power instruments that tracked atmospheric conditions, battery maintenance charging for telegraph or telephone systems, or backup lighting for critical areas like vault entries or stairwells. The air framing needs careful handling to avoid hype or pseudoscience implications. Atmospheric electricity is the accurate period term, referring specifically to the measurable voltage gradient between Earth's surface and the ionosphere. This is distinct from radio frequency energy, which requires different capture methods, from electromagnetic fields, different physics, and from various New Age or pseudoscientific interpretations. The systems were grounded in legitimate electrical science as understood at the time, even if their practical limitations made them economically unviable once better alternatives emerged. Museum collections occasionally preserve interior cabinet equipment from these systems, distribution boards with multiple insulated input terminals, protective arresters to prevent voltage spikes, storage batteries, and simple switching arrangements. These surviving examples show modest scale, cabinets 18 to 36 inches wide, shallow depth 6 to 8 inches, limited terminal capacity, suggesting 3 to 6 distribution circuits maximum. This is supplemental infrastructure for very specific applications, not primary building power. Engineering journal discussions from the 1900s and 1910s, accessible through historical periodical databases, show evolving professional opinion about atmospheric collection systems. Early articles are optimistic, describing experimental installations and theoretical calculations about potential power output. Later articles are more circumspect, acknowledging reliability problems, maintenance requirements, and the increasing availability of grid alternatives. By the mid-1920s, journal references to atmospheric systems largely disappear, replaced by articles about grid standardization and central station power distribution. The verification step here is to compare claimed capabilities to physical evidence. If atmospheric collection systems could power entire buildings, you'd expect to see much larger rooftop terminals, heavier conductors, bigger cabinets, and more extensive distribution networks. You don't. The modest scale of surviving installations confirms they served limited functions, supplemental, auxiliary, special purpose rather than comprehensive building electrical service. Here's what you can say with confidence based on physical evidence and period documentation. Buildings from roughly 1890 to 1915 sometimes installed rooftop atmospheric collection terminals with insulated conductor paths to interior regulation equipment and limited distribution circuits. These systems provided supplemental low-power electricity for specific applications where the modest, variable output justified the installation and maintenance costs. They were commercial products, systematically installed following documented standards, inspected by insurance underwriters, and maintained until economic and technical changes made them obsolete. What you cannot say without overstating the evidence, these systems powered entire buildings, represented revolutionary suppressed technology, or could replace modern grid infrastructure. The physical constraints were real and significant. The economic obsolescence was rational. Better alternatives, reliable grid power, standardized electrical service, falling electricity costs, made atmospheric collection impractical for almost all applications by the 1920s. The story is more interesting when you respect the limitations. Here was a legitimate engineering attempt to harvest ambient atmospheric electricity for modest building applications during a specific historical window when such supplemental systems had economic value. The technology worked within limits. The infrastructure was real, documented, and systematically deployed. It became obsolete not because it was fake or because it was suppressed, but because grid electrification offered superior reliability, scalability, and economics. The obsolescence was ordinary technological succession, not conspiracy. The evidence suggests a small, real, documented system with legitimate applications and significant limitations. If it were large-scale or revolutionary, you'd see different physical evidence and different economic outcomes. What you actually see is modest infrastructure that served its purpose during a transitional period and then faded when better alternatives emerged. The decommissioning sequence, how these systems disappeared from buildings between roughly 1920 and 1950, is itself evidence of what they were. Systematic removal follows predictable patterns based on economic value, salvage potential, and building modernization priorities. Decorative elements don't disappear this way. Functional infrastructure does. Start with what's missing. In most surviving buildings, the interior cabinet equipment is completely gone. Those rectangular shadows on corridor walls mark where regulation distribution cabinets were unbolted and removed. The hardware had salvage value: copper conductors, brass terminal blocks, porcelain components, cabinet metalwork. When building owners modernized electrical systems or updated interior finishes, this obsolete equipment represented material value that could offset modernization costs. Salvage receipts and contractor notes from building renovations occasionally itemize removed obsolete apparatus with scrap value listed. Conductor runs through attics and wall cavities are similarly absent in most buildings. The copper wire itself had resale value, and removing it during renovations was straightforward. Disconnect from the defunct cabinet, pull from conduit runs or unclip from standoffs, bundle and sell to scrap dealers. Renovation permits from the 1920s through 1940s sometimes include line items like remove abandoned conductors or clear obsolete wiring, generic language that doesn't specify what system is being removed but confirms systematic clearing of old infrastructure. Rooftop penetrations through parapets are typically capped or patched during this same period. Roof maintenance records show repairs to abandoned openings or sealed unused penetrations. Necessary weatherproofing work once the conductors passing through those points were removed. The patching materials, concrete, lead, bitumen, weather differently than the original stonework, which is why you can still identify penetration locations decades later by subtle color and texture differences. The rooftop terminals themselves often remained in place simply because removal costs outweighed any salvage or aesthetic benefit. A mast bolted to a roof platform, even if no longer serving any function, doesn't leak and doesn't create safety hazards if structurally sound. Removing it requires roof access, unbolting or cutting mounting hardware, patching the roof deck, and disposing of the metal work, labor costs that building owners often chose not to incur if the abandoned structure wasn't causing problems. This economic calculus explains why external shells persist while valuable interior components disappear: removal cost versus salvage value. Renovation permits and electrician work orders from this period, preserved in municipal building department archives, provide documentation of the decommission process without necessarily explaining what's being removed. Permits for electrical system upgrades or interior modernization from the 1920s through 1950s often include generic notes about remove obsolete apparatus, abandon in place, or patch and paint. The generic language reflects that by this period, the systems were obsolete enough that permit applications didn't need to specify details. They were just old equipment being cleared out during renovations. The cause and effect logic is straightforward. As grid electrical service became standard, reliable, and economically competitive during the 1910s and 1920s, atmospheric collection systems lost their economic justification. Maintenance costs continued, inspections, testing, component replacement, while benefits disappeared. Why maintain supplemental power when grid service is available 24/7? Buildings under renovation prioritized modern, standardized systems and discarded obsolete alternatives. The decommissioning accelerated during the Depression and World War II, when salvage value for copper and brass peaked. Code changes reinforced obsolescence. Electrical codes updated during the 1920s and 1930s increasingly standardized around grid-based distribution, phasing out auxiliary system categories. Insurance inspections shifted focus to grid electrical safety and eliminated requirements for supplemental apparatus testing. Without regulatory requirements or economic incentives, building owners had no reason to maintain or preserve atmospheric collection infrastructure. The pattern of disappearance is diagnostic: systematic removal of interior components, high salvage value, capping of conductor penetrations, necessary maintenance, abandonment of rooftop shells, low removal priority. This isn't random decay, it's rational economic decision-making applied building by building during a specific historical period. Compare this to how decorative architectural elements were treated during the same renovation era. Ornamental stonework, decorative brickwork, and architectural metalwork were generally preserved because they contributed to building character, and removing them was unnecessary. The selective removal pattern confirms these systems were understood as functional infrastructure that became obsolete, not as valued architectural features. The palimpsest effect you observe, exterior shells remaining while functional cores disappear, is exactly what you'd expect from economic decommissioning. The visible rooftop structures that remain are shells stripped of their internal conductors, disconnected from their regulation equipment, and no longer serving any electrical function. They persist not because they're valued, but because they're not worth the cost of removal. This is why appearance diverges from function. What looks like a complete system is often just the surviving framework, the functional components long since salvaged. Absence becomes evidence when it's systematic. If interior cabinets disappear from dozens of buildings during the same period, if conductor routes are consistently cleared, if penetrations are uniformly patched, that's a coordinated decommissioning pattern driven by economic and technical changes, not random loss. The systematic nature of the removal confirms these were functional systems that became obsolete rather than decorative elements or misunderstood building features. If removal is systematic, economically rational, and documented in renovation records, why did the interpretation shift from obsolete apparatus to ornamental feature? And when did that reframing occur? Stand on the same 1890s downtown commercial street where this investigation began, same bank block, same roofline, same afternoon light, angling across the brick facade. You look up at the rooftop tower again, but now the image has transformed. What looked like arbitrary decoration an hour ago now reads as a diagram of an obsolete system, elevated collection point, insulated isolation, regulated conditioning, limited distribution. The motif is clearer now because you've learned to see the whole sequence, not just the visible apex. The rooftop mast, with its crown of metal arms and ceramic insulators, marks the receiving terminal, designed for maximum atmospheric exposure, symmetrical geometry to balance collection, careful insulation to prevent unintended grounding. The parapet-level conductor penetrations, visible if you know where to look, trace paths from the terminal down to the building envelope. The interior routing, implied by mounting scars and attic standoff patterns, leads toward corridor cabinet locations where regulation equipment once stood. The distribution endpoints, now absent but traceable through conductor remnants and documentation, served specific building functions: indicator panels, instrument circuits, backup lighting, charging systems. You can still follow the evidence chain today. Photograph the rooftop hardware from street level. Request building permits from municipal archives. Compare physical measurements to patent drawings and catalogue specifications. Trace conductor stains and mounting scars. Match insulator profiles to period supply catalogues. Every step is verifiable, documented, checkable. The system was real, commercially available, systematically installed across building types, maintained according to code requirements, and eventually decommissioned when superior alternatives emerged. Now, the documentation trail is surprisingly robust once you know what terminology to search: atmospheric apparatus, auxiliary electrical systems, roof terminals, insulated conductors, protective devices. Period sources, engineering journals, patent records, building codes, insurance reports, procurement files describe these installations matter-of-factly, treating them as recognized infrastructure rather than experimental oddities. The historical memory loss doesn't mean the systems were imaginary. It means obsolete technologies fade from professional knowledge when they stop being relevant to current practice. Compare historic photographs where available. Images from the 1900s and 1910s often show building roof lines with more extensive hardware than survives today, confirming that decommissioning was systematic. You can see the progression. Early photographs show complete installations, mid-century images show partial survival, rooftop shells remaining, conductor hardware gone. Recent photographs show what persists after decades of benign neglect. The visual timeline documents exactly the pattern you'd expect from economic obsolescence. Valuable components removed, low-priority exteriors abandoned in place. The naming drift over time is revealing. What 1900s procurement records called atmospheric collection apparatus became roof equipment in 1920s renovation permits, then obsolete metalwork in 1940s building surveys, and finally decorative finial or Victorian ornament in recent architectural inventories. Each reinterpretation moved further from functional understanding and toward aesthetic categorization. By the time anyone currently working in historic preservation encountered these installations, the original context was lost, and the simplified decoration explanation filled the gap. The palimpsest effect, layers of interpretation overwriting original function, operates at multiple scales. Individual buildings lose interior components while retaining exterior shells. Professional knowledge shifts from system-specific expertise to generic architectural history. Public memory reduces complex infrastructure to simple ornament. None of these shifts required conspiracy or deliberate concealment. They're natural consequences of technological succession and memory decay over generational timescales. What you're left with is recognizable infrastructure hiding in plain sight, geometric patterns that make engineering sense, mounting hardware that matches documented components, installation practices that follow verifiable standards, and systematic decommissioning that aligns with economic and technical history. The evidence accumulates not because you're finding buried secrets, but because you're looking at familiar buildings with informed attention to physical details and documentary context. The final reflective line isn't about proof or certainty. It's about informed reinterpretation based on evidence. You can't prove with absolute certainty what every rooftop mast was intended for. Building histories are incomplete, documentation has gaps, and obsolete technologies leave ambiguous traces. What you can say is that the physical evidence strongly suggests functional atmospheric collection systems rather than pure decoration or simple lightning protection. That period documentation describes systems matching the observed installation patterns, and that economic obsolescence explains why they disappeared and why memory of their function faded. Obsolete doesn't mean imaginary, it means a better alternative one. Grid electrification offered superior reliability, standardized components, professional installation standards, regulatory support, and falling costs. Atmospheric collection systems couldn't compete on any of these dimensions. They worked, within limitations, for specific applications during a specific historical window. Then they became impractical and were decommissioned systematically across thousands of buildings over several decades. The infrastructure that remains is the leftovers, shells, scars, mounting points, and enough physical evidence to reconstruct what was there if you look carefully. You look up at that rooftop tower one more time, same building, same silhouette, same ceramic insulators catching the afternoon sun. It's no longer just decoration, and never was just a lightning rod. It's a surviving coordinate of an older system, traceable through patent drawings and supply catalogues, documented in building codes and insurance reports, and systematically installed across building types before economic and technical change made it obsolete. The city still doesn't know what it's looking at, but now you do.